Thank you everybody for coming. Our first week of the seminar is Bulent Tosun, who will tell us about contact surgery and symplectic fillability.
Thank you so much. Thank you, Shira and Vinay, for the invitation and everyone for coming. I can see also Bahar, an old friend, or Zoom. So, as the title suggests, my goal today is to tell you about contact structures that arise as the boundary of symplectic manifolds. And I would like to start by kind of, making a small introduction, setting the scene. So for today, I will take like psi to be a closed, co-oriented contact free manifold. Everything I will talk about today is in low dimension. So by co-oriented, I mean we would like to write this psi as the kernel of a one form, a global one form, such that alpha vec d alpha for this one form is a positive multiple of the volume form. So in particular, we are really interested in positive contact structures. So as an example, maybe think about S3 with a so-called standard test structure, which is given by the kernel of this particular one form, where I choose x1, y1, x2, y2 as the coordinates on R4 that S3 sits in. So the goal in contact geometry in low dimension is to understand these objects. Given any three manifold, list this contact structure and understand the interactions with low dimensional topology, with the symplectic geometry, with differential geometry, anything you might imagine. So in principle, there is an algorithmic way to understand this. It is due to a theorem of Binka and Gargas that says that indeed, by what's called an operation of contact surgery, you can understand any contact three manifold starting from this three manifold. It goes exactly like this. Any y psi can be obtained from S3 psi standard by what's called contact surgery. This is an operation of surgery which comes with certain coefficients, in which you can choose the coefficients to be plus or minus 1. And the complexity is here along what's called a Legendrian link. So with this theorem at hand, so one of the natural questions you might ask is like, given a contact surgery presentation of a contact tree manifold, what properties we can read of? What could you say about whether that contact structure is, let's say, fillable, namely whether it arises as a boundary of a symplectic manifold or maybe a compact complex manifold? Or you might wonder whether we can determine if the contact structure is tight, a class of contact structure that is geometrically very interesting, or you might be interested in various invariance contact structure might have in Fuller homologies that come from gauge theory, or maybe ECH, or maybe various contact homologies for contact structures, but even for Legendrian transfers not inside the three manifold. So my focus in that direction will be on what's called the symplectic fillability, and that is what I would like to little bit say about. Focus for today will be symplectic fillability. And I would like to kind of briefly remind you what I mean by this, so that we're on the same page. I will mostly use the cartoon pictures. I'll talk about three types of the fillability. The first one is what's called the weak symplectic fillability. And this is what this is that cartoon picture, if you wish, is that we have our contact manifold like psi, and we're looking for a compact symplectic manifold that fills this. So as by kind of the cartoon picture, the boundary of this x should be y, and we want some compatibility between omega and psi, and it is the weakest form you can imagine, namely that it evaluates positively on the contact lengths. So the second type of the fillability I will talk about is called the strong symplectic fillability. So this is essentially this, except that we also require some dynamical properties near the boundary, namely that now our y psi arises as the boundary of this x omega, this compact symplectic manifold. Boundary x is still y, but now what we require this existence of so-called Liouville vector field, namely a vector field available near the boundary, transverse to boundary, such that this flow preserves the symplectic flow. And once you have this, indeed, even the contact structure is determined, it is given by the kernel of the contracting the symplectic flow along this vector field. So this vector field is kind of the available in a neighborhood, maybe such. The final type of the fillability I will talk about is so-called the Stein fillability. So here, now we are talking about a compact complex manifold. So what I'm talking about essentially is this data of a compact complex manifold X. Its boundary is still Y, my contact tree manifold. But this is decorated further. It has a particular Morse function, phi. What is particular about it is we want it to be J convex. So of course there has to be J in it, which is a complex structure on this. So and this J is also responsible to produce this contact structure, namely psi is exactly given as the complex tangencies of this complex structure. Okay. So you really should think about this one in the background. We have a Stein manifold, which are necessarily non-compact. But what we are doing, we are taking a sub-level set of that Stein manifold is this data sometimes called maybe less emphasized. This is a compact Stein manifold, and this data is typically this triple is called a Stein domain. So we are taking a compact piece of a Stein manifold, where Y arises as the convex boundary of that sub-level set. So Kähler structure is built into this manifold. So once you have this data, you can automatically talk about what's called a symplectic form, which is given by just minus d of the d phi composed with J, and then this also produces you a metric in a kind of natural way. And then if you take the gradient of this phi with respect to that metric, that produces this Liouville field here. So all this to say that implication C implies implication B, or the property C implies B, that implies A, and each of these implies that indeed the contact structure is tight.
Remind me what tight is.
So tight is this contact structure where in here you cannot find what's called an over-twisted disk. Namely, you cannot find an embedded disk where along the boundary contact planes stay kind of tight, stay tangent to the boundary. So it's a property you're trying to avoid. You're trying to avoid to have an overtwisted disk inside your manifold. And it is that one that is intimately related with the topology of underlying tree manifolds and other things.
Yeah, so this disk happens if you look at the local picture of a contact structure, so the planes have to twist, and if they twist more than they have to be not integrable, so they twist over, then you find those small disk of that type.
Actually, it's used in a completely different context in what I'm doing, and I wondered if I just wondered if it was related. I think it's not.
So let me give you an example of a kind of like, just because I talked about the S3 over there, if you take the 4-ball together with the usual complex structure on C2, I'm thinking about it sitting inside C2. And then if you equate with this particular J convex function phi, I will take it the z square over 4, just so the math is correct, some normalization. This is indeed, this triple is a Stein filling of that twist field with that tie structure. I will here also insert what is this symplectic form. It is our kind of below symplectic form, the standard simplex structure on B4. This one is a Stein and hence symplectic filling of this S3 with a standard contact structure. Indeed, it is the only one of the symplectic like this. Good. So, the question here is then, as I said, the focus will be on symplectic fillability. The focus is that when is fillability preserved under contact surgery? And I already have a good answer to that. Maybe I'll move on and state it here so that I can keep that section for results. So here's what is known. So about when is that fillability is preserved under various surgeries. So the setup will be here that I will take Y side to be a contact 3 manifold. I will take K to be a Legendrian knot inside this contact manifold. Okay, so here is a result due to Eliashberg. It is rather general, and it says that essentially when surgery coefficient is negative, any type of fillability is preserved. So if Y side is fillable in any of this sense, in any sense, then contact R surgery along K is fillable whenever R is negative.
Are we doing rational surgery?
So here R is any rational surgery pure or true. Okay. I didn't talk about the operation of contact surgery, but just very briefly, it is, in a sense, you should think about the usual dance surgery where instead of the specifying framing coming from the cipher surface, if they're not non-homologous, the Legendrian knots, they have canonical framing coming from the contact structure, we use that. And if your knot is really non-homologous, the difference between ciphered framing and contact framing is captured really well. It is a single integer, so-called the Tosun-Banneker number, easy to calculate from the Legendrian. This kind of the passage will be useful for us. We can always go in between if you need to. Yes.
That also holds for exact fillability.
Exactly. So this really so there are intermediate kind of the types of fillability, this is fine, that's fine, everything in between is fine too. Yeah. Good. So okay, when you do negative surgeries, no restrictions, nothing. You kind of essentially you extend fillability that is available on the domain manifold. So the question is that what happens if you have positive surgeries? So this is where things really could go bad. So you could potentially perform a contact surgery with positive coefficients and convert a Stein fillable object to something over twisted. It could be very harmful. So, but still, you could also find examples that contact surgery produces something fillable. So the question is that, okay, can you characterize it? So here is a kind of example or like a theorem in that direction. So this is a work some years ago, James Conway, John Etnyre, and myself proved. And this says the following point. It says that although it is true in general contact tree manifold, I will tell it how it works in S3. If K is a Legendrian knot inside S3 with this standard type contact structure, then the following is true. Then contact plus 1 surgery is fillable, is symplectically fillable in the second sense. Whenever I use symplectic, I will drop the strong from the description. Symplectically fillable if and only if L bonds or K bonds a Lagrangian disk. inside the four-ball with the standard symplectic structure. Okay, so yes, contact surgery with positive coefficients could be harmful, but if you satisfy that at least for contact plus one surgeries, you can certify symplectic fillability. And indeed, if you decorate this Lagrangian disk somewhat, you can upgrade symplectic fillability to Stein fillability. Good. So, after having this result, we were really interested to see how could we improve this to obtain higher surgeries. So we had some ideas. This is why I will keep this result also on board as we go along. But then the actual answer was a bit surprising even to me. So let me state the main theorem of the talk. So what happens when the surgery coefficient is greater than 1? So I won't be able to answer this for you for all positive integer surgeries. And you might ask what happens in the rational case. For various kind of the practical results you have in contact geometry, often you can upgrade this easily to rational case as well. And we'll talk about it when we come to the details of the surgery coefficient. But here is the main theorem. And this is joint work with, and everything here is joint work with Tom Mark. And this is from earlier this year, and here is what it says. It says there exists an integer and positive such that I will use this notation psi and k. This means that I am doing contact and surgery along the Legendrian knot k inside the contact tree manifold y psi is weakly filled by some symplectic manifold, z omega. I guess I call it z prime omega prime, if and only if the following two conditions holds. Okay, so here maybe let me say that k is the Legendrian knot inside y psi. Okay, so here are the two conditions. The first one is the domain manifold must be fillable. And here is kind of something that will look like parallel to that, which is that not just that it has to be fillable, but also in a filling, or there exists a filling, I will call it z omega of y psi, the domain manifold, that contains, and also maybe let me insert here a weak filling as filling z omega of y psi, containing a properly embedded symplectic disk, which necessarily has a transverse boundary, but it's not an arbitrary transverse boundary. It has something to do with this k. I will call this disk delta all along inside the z, where its boundary is a transverse knot inside the contact tree manifold is nothing but what's called the transverse push-off of the Legendrian knot. Is a positive transverse push-off of K. Okay, so there is more to this. Indeed, this symplectic filling z prime omega prime is characterized. It kind of it arises only in one way. Let me add that. Moreover, we can choose z and the symplectic disk delta such that this z prime omega prime.
So it would be, if I look at the disk, the boundary of the disk nearby. So I would first say take a disk of which is bounded by k.
Yeah.
And then I have sort of this band around, and that is what one uses, and then extend it, and then for generic band, I would have that the if I push off that node, it would be a transversal.
Correct.
Yeah, so
Exactly.
that
And it
is-
is unique once you specify the sign.
Yeah,
Exactly. So this symplectic filling tank, you can choose the n omega such that it's a symplectomorphic. So this is the meaning of this one, which is given as the removing a suitable neighborhood. Maybe let me use neighborhood notation of D from here, and symplectic form omega prime is nothing but this restricted to this complement. Okay, it's extremely important that this develops like this. It will be very useful in applications. Okay, so this is the main result. So necessary and sufficient condition for a positive for a contact surgery with positive coefficients to be fillable. So okay, so here's what's going to happen. Here's the outline for the rest of the talk, more or less. So I would like to tell you a few things about I want to unpack this theorem, and I would like to say some examples of case on which indeed contact surgery with positive coefficient produces fillable, namely that this is not like a trivial result. Second, I would like to talk about some constraints that, restrictions the way that we saw it over there. And then I would like to talk about, in each of these cases, some topological consequences, purely topological. And finally, you might have realized that I'm really not being very specific with the surgery coefficient. I'm saying there is some integer n. What is it? So I would like to also give you some lower and upper bounds for that surgery coefficient. You will be and we'll be able to say a lot. So, and for me to be able to do all of this, I would like to specialize in a very particular domain manifold, where I already know what are the symplectic fillings. And it's not a surprise. I will, of course, focus on the case of when YXI is the S3 with the standard contact structure. It is perfectly fine that you focus on length spaces. Their fillings are also understood, or maybe certain separate fiber spaces or other three manifolds. So let's look at that. Maybe I have already a clean board. Let me go with that. Okay, so let's look at some examples. But before I do that, let me do the specialization. For today, I will specialize in when YXI is exactly S3 with the standard contact structure, and K all along, as you see, I use it for a Legendrian knot, but sometimes K will be just a knot type. And when I say that K has a fillable surgery, I mean that it has a Legendrian representative which admits a fillable positive surgery. Okay, so just because this is a board talk, I will be a little bit imprecise, but I will try to be careful when I say something. Okay, so we will specialize in this, and there is only one purpose for this really. This is this key fact, which is due to Gromov and independently McDuff. And the result says that while we do know what are the fillings of this, every symplectic filling of this manifold is nothing but it's a blow up of the four-ball. Is of the form or equivalent to four-ball blow up some number of the times. Okay, for some K. Okay. First, we start with the standard symplectic structure of four-ball. It is that one that you're blowing up. Okay, so this is very useful. So now, once I have this, I can already rephrase my theorem, right? It becomes much shorter. So when I say this, then the main theorem becomes the main theorem over there says, in light of this result, is that K has a fillable positive surgery. Namely, there is some Legendrian representative of K for which some positive integer, some contact surgery with positive coefficient is fillable, if and only if the following is the case: is transverse push-off. The transverse push-off of this bounds a symplectic disk, properly embed a symplectic disk in the blow up of the four-ball. Okay. It's just rewriting this because now fillability is obvious for white psi and we have exactly what is the filling. So here is a topological consequence of this right away. And this is the following one. It says that, well, if psi and k is fillable, so if psi and k is fillable, then any filling of psi and k has negative definite intersection form. In particular, the tree manifold here bounds a negative definite form manifold. So this result, if you have some Hager-Floor people, they will be very happy. This result is true if the tree manifold you have is an L space, namely that any symplectic filling of a tree manifold that's a Hager-Floor L space, then it must have a negative definite intersection form. But here there is no restriction on the tree manifold. It doesn't have to be an L space. So it's a non-trivial topological consequence here. And indeed, often examples of knots that have fillable surgery that we will find, they actually are not L spaces. But of course, there is a little bit restriction here. The restriction is on the contact structure. So we cannot quite say that any symplectic filling of the tree manifold with whatever contact structure you choose must be negative. That is slightly stronger. There, understandably, you need to have an assumption, namely L space assumption. Okay. So good. So we have this one. So now let me make a remark, and this remark will be extremely useful. I would like to rephrase this result slightly different. So for that, I would like to make the following remark. So you see, if you start with a symplectic disk, a smooth symplectic disk, or even smooth disk inside a blow of the foreball, what you can do, you can try to blow down and try to reach out in general a singular symplectic disk or disk inside the ball itself. Okay, so let me kind of write that process and kind of to see how in the case of symplectic disk that's kind of the that gives a useful criteria. So if I start with like maybe this, which is inside a blow of the foreball, is the symplectic disk. Okay, for now I will just start with a disk, a smooth disk. So then what I will apply to this, I will kind of blow down the CP2 bars, and then what I will get another disk, delta prime, I will call it. This is, in general, is a singular. I mean, it doesn't have to be singular. It's possible that this disk is not piercing any of the disk exception occurs from the CP2 bars. In that case, they are there for no reason. But if they do, in general, this is a singular disk, and it will have a bunch of singularities. This will be nothing but certain multiple points with some order. But you can always perturb it, disk, which after perturbation can be assumed to have only double point singularities. Maybe you have a singularity of order 3, you can perturb it and obtain 3 double point singularities. Okay, but again, if the disk at hand is a symplectic one, you can actually do better. And that is what I would like to write here. Here is a rephrasing our main theorem here. The main theorem reads or says, indeed, K has again, K all along is now not inside a strict size standard. We did that specialization, has a fillable positive surgery, if and only if. What we can say is that this transverse push off bonds an immersed symplectic disk with, so here is the key part, with only positive double point singularities. Okay, so the really emphasis here is on this kind of the double point singularities are only positive, and the reason for that, if you start with a symplectic disk inside the blow of the four ball, indeed you can choose an almost complex structure compatible with the symplectic form, for which disk and exceptional curves are both holomorphic. In particular, when you look at the way that these disks intersect each of the exceptional curve, it has to be, the geometric intersection has to be positively contributing to the intersection number. So, and that is the reason when you kind of came to like an immersed inside the four ball. So this is inside the four ball. So you can really arrange that the singularities have the holomorphic charge. So this is kind of very important. And this essentially follows from earlier work of McDuff and used in other places too. Okay, with all this, I'm ready to now talk about some examples. Here are some examples. So what are some nuts on which we can certify that we have positive fillable surgeries? So the first example is like this, some examples. Okay, so example number one, length spaces. So if K, now suddenly you realize that here I will take K to be a topological nut, but hopefully from the context it will be clear what's going on. If K admits a length space surgery, that means that some smooth P surgery, this is smooth P surgery on K, is some length space LPQ. Okay, then K admits, or K has a positive fillable surgery. K has a positive fillable surgery. So, and this essentially follows from a few observations. One is that how this surgery coefficient that gives you the length space, how it interacts with the genus of the knot in the tree sphere, and how Thurston-Banach number of such a knot is comparable to the genus of the knot. And then using an early result of myself and Tom to certify that indeed contact surgery, relevant contact surgery has to be tight, but because you're on L space or length spaces, all tight structures are fillable, and that is the result. So I will not kind of expand much on that. It's really kind of comes quickly because other examples are a little bit more illuminating. I will spend more kind of giving explanations, arguments for that. And here is a second example. So if your K is actually closure of a braid, a particular braid, closure of a braid, a positive braid, where beta is a braid on braid index n, but crucially I assume that, or I want it to be positive, a positive braid. So then the claim is that K has a fillable positive surgery. So let's explain how this goes. So what's the idea here? So the key point is this algorithm that we will use due to Boileau and Weber. And the point here is that, okay, if you start with a braid, arbitrary braid, it doesn't matter, it doesn't have to be positive, it doesn't even have to have closure to be like a single component, it could have multiple components. What Boileau and Weber produces, they produce an unknotting algorithm for braid closures. And the idea is that essentially they kind of convert certain number of crossings from positive to negative or negative to positive, and they produce here another braid so that its closure is actually unknotted. So a very useful criteria if you think about it. So in our case, we're going to use this algorithm, but we have some advantages, namely that our braid that we are starting with is actually a positive braid. So here's what happens then. So you start with this kind of maybe braid closure, beta bar, which is a positive braid closure. So Weber algorithm, what it will do, it will switch some number of the crossings in this positive braid. And of course, because this is a positive braid, when the crossings you are switching, you're necessarily switching from positive crossing to negative crossing. Combined with some transverse isotopies, this operation produces this trace produces an annulus. So in this end of it, we have epsilon bar, which is an unknotted, it's a braid with unknotted closure. But remember that we switch bunch of the positive crossings. This annulus potentially has bunch of positive double points. Okay, so good. We have an annulus which has bunch of the singularities modeled on the double point singularities, positive double ones. Now this epsilon bar is an unknotted curve. In particular, it's a transverse unknot. This is a transverse unknot. But which one is it? So by that I mean we are interested in the self-linking number of it. This algorithm is explicit enough. We can actually calculate the self-linking number here, which is essentially the word length here we have minus the braid index. And when you calculate it, this transverse unknot actually has self-linking number -1. So you recognize that this is the one that it actually bonds a symplectic disk. Capped at it, and here is your immersed disk, symplectic disk with positive double point singularities. This says that B bar, beta bar has a fillable surgery. So this is kind of our first step into the world of braids and braid closures. And of course, when you did that, I assume almost all of you here will immediately remember this beautiful and deep connection between what's called the class of quasi-positive braids and symplectic topology, which is in work of Boileau or Evkov and Rudolph earlier. We know that quasi-positive knots, those that they arise as the closure of positive braids, are exactly those that they are obtained as the transverse complex curves, namely they arise exactly as the intersection of a complex curve and S3 inside C2. And there's a further result of Boileau and Orevko. They say that indeed, if you have a symplectic surface, inside the foreball, then the boundary or the surface is quasi-positive. In particular, the boundary of the surface has to be quasi-positive. So good. So having that, let's see that how that impacts our results. I would like to give you a couple other examples, but along the way also maybe some obstructions. So let's talk about that. So let's look at the connections between quasi-positive braids and symplectic fillability. So I would like to here state a theorem. This theorem will have two parts. So let me write. So all along here, I will assume that K is a knot inside S3. So it is the first part. It will have like some condition here. For me to implement that condition, let me make an observation here. Here's an observation. So we did talk about having a symplectic disk inside the blow of the foreball. We talked about potentially kind of the producing an immersed symplectic disk out of it inside the foreball. But there is one other thing we can do. If you have an immersed symplectic disk inside the foreball, we can actually produce a symplectic surface out of it. And we also have a control on that symplectic surface. Namely, if I have sigma, which is inside the foreball, let's say with symplectic immersed symplectic disk, we assume that we can kind of make all the singularities to be double points. Let's say that it is with m positive double points, with m positive double points. Now, what you can produce out of this, you can smooth these double points. For each smoothing, you will pick up one genus. And then you will produce here a symplectic surface, smoothing the double points. And this symplectic surface will be some surface, it will have genus M, right? Because there were M double points to smooth. But then, symplectic surface, by the resolution of local Thom conjecture, they are genus minimizer in their homology class. That means that the genus of this symplectic surface is determined actually. Symplectic surface with genus M, which has to be equal to what's called G star of K. What is this G star of K? This is nothing but this is the slice or four-ball genus of the knot K. This is the slice, or some people call it four-ball genus of K. Okay, so good. So this observation is important. So now, with this, it is a trivial observation. If you take that fact and our theorem and a result of Boileau or Evcourt, which is that K has fillable surgery, implies that means that there's an inverse symplectic disk with positive double points. You smooth these points and you get a genus G star symplectic surface. Boileau or Evcourt says that then the boundary of that symplectic surface must be quasi-positive. Then K is quasi-positive. Again, here I'm really kind of being careless. What I mean is that the transverse push-off of K is quasi-positive. Okay. So this much is okay. There's not much to do. So what is missing here? If I assume K slice, namely that if its slice genus, four-ball genus, is exactly zero, indeed the converse is true as well. You have a fillable surgery exactly when you're quasi-positive. As I said, one direction is obvious. The other direction is that if you are quasi-positive and slice, that means that you are bonding a symplectic surface, but you're also bonding a smooth disk inside four-ball. But symplectic surfaces are genus minimizers, so you must have genus zero symplectic disk, and that is the other direction. Okay, so far I have explored quasi-positivity as something that very, very symplectic geometric terms. Like it is those that they are transverse complex things, namely they arise as the intersection of complex curve with S3 and size C2. But of course, like those who studied quasi-positivity in braid theory sense, these are those that they're not quite positive braids, but they are, if you look at the braid description, they are written as the arbitrary conjugates of the standard generators. Okay, very, very controlled description as a braid group. With that in mind, we can actually do better than this, in the sense that if not is not a slice, we can actually still give like a rather satisfactory results. And here is that. So let me kind of derive another theorem. So we can do better, and that will be the second part of that. So two. So here is that. So let me see how I wrote it. So here's the kind of the second statement. It's a following if and only statement. K has a fillable positive surgery if and only if K is of the form B closure for some quasi-positive braid, And of course, there is no sliceness assumption. You must kind of be suspicious. Okay, what about this quasi-positive braid? K is of this form closure of a braid, which has what's called quasi-positive braid expression. I guess this much is okay still. But here are the conditions on this that will certify, it doesn't matter you are sliced or not sliced, you will have fillable surgery. Containing exactly this, containing two things. Exactly, and by the way, let me emphasize, this is a braid with the braid index n. That is important, that n. So this quasi-positive braid expression will include what's called exactly n-1 positive nodes. This is something I'm going to tell you just in positive bands. I'm going to tell you just in a bit. So, and second, the rest the rest are what's called our positive nodes. And I will tell you what is that as well. Okay, so somebody will give you a quasi-positive Braid expression, namely you have a bunch of Braid generators, standard ones, and bunch of them include arbitrary conjugates of the dead generators. So in there are those you will identify as positive bands and positive nodes. With this configuration, if they are in the right place, we can actually certify fillability. Let me kind of say what is positive band and positive node and what is the relation of this to symplectic fillability. So here it is. So here is some terminology first. So for this terminology, I will choose sigma to be a standard Braid generator. And I will choose W to be just a word in the Braid group. I don't care, just a word, okay? Made of the positive or negative generators in whatever form. So here is the notation. We say W sigma W inverse, arbitrary conjugate of this one. We call this is called a positive band. Okay, and if you have a kind of expression on the following form, omega W sigma square, a square of the generator, W inverse, this is called a positive node. Okay, so what's the relevance of this one? So if you start, this is work of Rudolph, I will say plus bunch of epsilon, which says the following one. If you start with a K, which is closure of a positive, closure of a Braid, with quasi-positive Braid.
Sigma would be standard generators.
Yes, standard generator.
Oh, yeah. Okay.
Yeah, it's just a standard generator.
Okay.
Braid.
Okay.
Yes. So if you start with a quasi-positive Braid, you look at the Braid expression. Rudolph, what he produces out of this, it produces a smooth symplectic surface, indeed an algebraic one out of this. So it produces, I will not emphasize on algebraic aspect, it produces a symplectic surface. Okay, so this symplectic surface that we produce out of this bonding K, the Braid closure, and I can be specific about this symplectic surface. What is the data goes into that, like how it is built. I will be able to describe you handle by handle what it is. So that is the following one. So I already erased the first part. So this surface is this, where Braid strands are in one-to-one correspondence, or you exchange them with the disks. And then positive bands are replaced with one handles. And positive nodes are replaced with the positive double points. So the epsilon part refers to the decay. Rudolph, in his original kind of the study of this one, he only focuses on those that they are smooth. So this is kind of the epsilon part where you can actually look at the singular ones as well. And okay, so you start with this kind of the quasi-positive Braid expression, and you obtain a symplectic surface. So now, what is the point of the death theorem? So what we want in our case, we want to build a symplectic surface, possibly non-singular, but with positive double points. But we also want this to be actually not a kind of the positive genus surface, we want it to be a disk. And this condition, having exactly n-1 positive bands, guarantees that. Just guarantees that you will always get a disk out of that process. So this turns out, this kind of criteria, it turns out that to be extremely effective to actually detect the fillability. Here is an example, for example. So here is is a knot, 10 crossing knot 10142. You just go check it from the knot info. It's a quasi-positive knot, namely that it is the closure of this quasi-positive braid. Okay, as you see, it is mostly standard generators. They might repeat, but then you see like a conjugate of one of the braid generators. So I look at this and I would like to say that whether this is in the form that is acceptable to my taste, so that I can certify that some positive surgery on that knot is fillable. Well, remember that this, if you look at this one, this is actually this is in B, it's a 4-stranded braid, right? So in particular, to apply my theorem, the number of the positive bands has to be exactly 3. Okay, so remember that positive bands are those. So first thing, when you look at a braid expression like this, you need to separate squares because these will be positive nodes. Here is a square, here is another square, separate them. They will be just squares. So what is left? You should have exactly 3 either standard generators or their conjugates. How many I see is 1, 2, 3, 4, 5. Too many. This is just too many. Too many. Too many positive bands. So what you do, you don't panic. You just try to kind of implement a bunch of braid relation and reorganize the braid. And this is the kind of a little bit unfortunate part of this one. A braid could have, or a braid closure could have many different braid descriptions. So here, it's really very simple. You just do a very, very simple, only one braid relation. You apply that, and if you do that, you will get this braid. Now, if you look at this braid, let me separate the positive nodes and then look at the bands. So here's a positive, here's a positive, here's a positive. Ignore them. What is left? We have conjugated sigma 1 here. This counts for 1 positive band. And we have another band, and we have another band. It could be conjugated with the just identity element. That's fine. So now we have 1, 2, 3 bands. That in particular says that we are in the kind of the situation of this theorem. That means that we can certify that indeed beta closure has, which is the knot, this one, has fillable positive surgery. So the importance of these positive nodes will be that they will impact the surgery coefficient. So for example, having 1 square contribute 4, and the second one, third one, this says that 12 surgery on this knot is indeed symplectically fillable. It might not be the optimal one. You might find something smaller, but 12 surgery for sure is fillable. Okay, so far so good.
What about a higher? Can you take N big?
N?
Yeah.
Yeah, I mean, so let me add another example since you asked. This algorithm is efficient indeed. Here's an example of the second statement there. So here's another example. Maybe this is the first one. Here's the second one, which is that out of, so you see, we wrote the quasi-positivity is an obstruction for fillability. If your knot is not a closure of quasi-positive braid, you have no chance to be fillable. Now, out of, I don't know, through 10 crossing knots, out of, through 10 crossing knots, there are 59 of them that are quasi-positive, okay? Out of, these are the only one who could have fillable surgery, okay? Out of 59 through 10 crossings, I'm just going through, I don't know, your favorite knot table, all the way to the 10 crossings. I list all the quasi-positive ones. There are this many. 48 of them, 48 of them are fillable. And it's exactly because of this criteria. You just go ahead one by one, put them in the right form, it has a fillable surgery. And in many cases, we can also be optimal.
And the others are.
And 11 are not. Are fillable or have fillable surgery, and 11 do not. Okay, and so that means that quasi-positivity is not enough to certify that you cannot be fillable. So you can be really efficient, and you know the only reason we start at the 10 crossing just because we just want to implement our kind of the strategy. You can easily go to the higher crossings if you wish. Yes.
How do you make sure that it does not have a fillable?
Yes, that motivates the next part, right? Now let's talk about the obstruction, like constraints on K. And that kind of actually has even more topological consequences. Let's talk about that part. I wish I didn't erase this, I'm sorry. Because this is not the board I will use anyways. Terribly sorry. If you ask me, I can draw it again. So this is not the board I want to use. But since I erased it, right? So here are the constraints. This is the third section, I guess. Constraints on the knot. So for this, I would like to make a definition. So here's the definition. And definition goes like this. I will talk about what's called the four-dimensional clasp number. The notation I would use is C of K of a knot K inside S3. And what is that? The four-dimensional clasp number is the
CLAS.
CK.
No, clasp.
Clasp, yeah. So what is that? It's the following quantity. It's the minimum number. Minimum number of double points, positive or negative, I don't care. It's a smooth invariant. Double points in any immersed disk. In fillable that K bonds. At all possible immersed disk inside the fillable that K bonds, you can always make the immersed points to be double points with sign, and the minimum one is your class number. Okay. You can always smooth the double points to get a smooth surface, but that might not be an efficient way. Here's an observation, just a little note. CK is in general greater than or equal to the slice genus. But this inequality could be sharp. Indeed, the gap between the class number and slice genus could be arbitrarily big. This is recent result of Uhaus and Zemke using K-graph floor homology, and also some instanton floor homology by Daemi and Scaduto. They find examples of knots where the difference between class number and slice genus is arbitrarily big. So far, so good. It's just a topology. Here is an obstruction that is extremely efficient. It's the following one. Too many boards. Okay, so here's the first constraint, which is that if K has a fillable positive surgery, then it must be that its class number is equal to slice genus. And that is enough to answer your question, Thomas, to prevent all of these 11 examples, for example. So, good. But this has more to say, something to my surprise, very interesting. So, this is extremely efficient. So, here's like a kind of example that, like, you know, we came up with this example very, very early on when we were doing this research, and it completely changed the entire content and direction of the paper, which is the following point. Consider the following simplest possible knot, really, one of the simplest. So consider the knot K being the so-called the 7-4. It's a 7 crossing knot in the knot table you encounter. What about this knot? Well, this knot has a bunch of properties. Let me list that. So this knot is positive knot. That means that it has a diagram that has only positive crossings. But it's not a positive braid closure, it's just as a positive diagram. But that is enough to certify that knot has to be quasi-positive. Okay, so and hence it is quasi-positive. That says that this knot actually bounds a symplectic surface inside the foreball, right? It does have this property. But it is interesting, it actually bounds a Lagrangian surface inside the foreball. Indeed, K bounds, let me emphasize now, 7-4, bounds a Lagrangian surface inside the foreball. Okay, so I would believe when I kind of came up with that result with Etnyre and Conway that bounding Lagrangian disk gives fillability for contact class 1 surgery, then higher genus Lagrangian surgery should be responsible also for fillability. I would imagine that surely this knot has fillable surgeries, right? It bounds at a very relevant object. And let's add more to that. Indeed, any positive contact positive surgery on this knot carries a tight structure. So any positive contact surgery on 7,4 is tight. This follows from, for example, my earlier work with Tom Mark. But if you look at what is the class number for this knot, you find that it is 2. On the other hand, its slice genus is 1. And that is bad, right? That says that there is no fillable positive surgery on this knot, no matter which surgery you choose. There is right contact structure, there are tight structures, and it bounds the right kind of the symplectic and Lagrangian objects inside the four-ball, but not good enough. So if you try to kind of look at a possible, symplectic surface, you cannot realize one immersed one with only positive double bonds. You cannot. So this is something, and here's a completely like a topological corollary, another corollary. And I don't know any other proof of this other than going through our theorem, which is that you remember that one of the earlier example was that if you're not admits a lens space surgery, then we said it has a positive fillable surgery. That combined with this result, I guess that result over there, sorry, this result here, that says that if K has a lens space surgery, then C of K must be equal to slice genus of K. So this is the topological consequence of our work. And as I said, I really don't know any other proof of it. So knots that they have lens space surgery, they are very interesting for low-dimensional topologies, mainly because there's a proposed class of knots which should kind of give all possible surgeries to lens spaces. If a knot has a lens space surgery, so-called Berger knots. So this kind of was in the vicinity of the thinking about that conjecture. We couldn't progress on that, but that was the relevance. I guess I promised you that I will also talk about the surgery coefficient. I couldn't. I'm already a couple minutes out of time. I will just kind of say the following one. I'll say that this is just one line, and if you want to learn more about it, talk to me, which is that I can be specific about minimum surgery, fillable surgery coefficient. If mu k stands for a not inside S3 as the minimum, being very imprecise here, minimum fillable surgery coefficient. And of course, I should be careful if exists, right? It's possible that if your knot is not quasi-positive, you don't have this, then I will define this quantity to be infinite if it doesn't have any fillable surgeries. But if it is finite, you can prove that indeed the interval of the fillable surgeries is an infinite interval, with minimum being this one. I can say this much about this mu k, which is that this mu k, there is a little fact or theorem in our paper that if mu k is finite, meaning you have fillable surgery, then this mu k is indeed less than or equal to 4 times the slice genus of the knot, and it is greater than or equal to twice the slice genus of the k. It can be this specific, but unfortunately, we cannot do better than that in the sense that slice genus or genus or anything else we know doesn't quite pin down this exactly. It is in this interval, and indeed, if the one thing you see here that if the knot is sliced, then of course
for both.
We do. Yes, indeed, you can often find it as this, but you can, if not is not sliced, let me add this here. This is strict if K is not sliced. But of course, if K is sliced, you see you have 0 and 0. So if it's sliced, you know that that minimum surgery topological is actually 0 surgery. And that's the best we can do. So yeah, I mean, I think I'll stop here. I have questions, I can say some more, but.
Yeah, I have a philosophical question. So we know so much about the three manifolds.
Yeah.
Can you, do we know that if we, without invoking Paramon, on a homological three sphere, we have a tight context structure? On a homotopic.
So there are lots of homologous spheres. Well,
No, I mean homotopic sphere.
oh, without.
Paramon.
Huh. So your question is a little bit difficult to answer because if you focus among cipher fiber spaces without using any panel or anything, there is one homologous sphere that doesn't have tie structure, Poincare sphere. It just doesn't have. Well, it doesn't have in the sense that it doesn't have a positive contact structure. But if you focus, you don't care positive or negative, then that one has a negative contact structure. But then there is the class of hyperbolic three manifolds, and you could imagine building many homologous spheres out of that. Just do a 1/n surgery on a hyperbolic knot if you wish. Unfortunately, the state of kind of like whether
So we have so many machineries, but we can't capture what three-dimensional space is from that direction. Yeah?
Exactly.
Which Paramon in some sense captures.
Well, but Paramon work is not enough.
No, it's different, but there's a big gulf between. I mean, it's.
I think it is correct. I think I understand what you're saying. You're asking, could we have something like an analog of Paramon's result?
There's always machinery. Would there be a way? I'm sure people tried, but it obviously.
So it's yeah.
Didn't work, and I wonder what would be interesting to know is what doesn't work.
I think it's just really hard to come up with the characterization of the tightness. It's very, very tricky.
Yeah.
So we have also very strong invariants to detect tightness, but they always work one way. So this often looking this kind of constructions coming from surgery, they are the most kind of the user-friendly you can hope to progress, so as we did here. So, but in general, it's really, really tricky. But it also doesn't say anything bad. It just says it's really rich structure. It is kind of the answers are really deep into the. Yes.
So everything you described is for Legendrian surgeries. What about transverse surgeries?
So by Legendrian surgeries, like sometimes people use the Legendrian surgery to mean negative contact surgery. You mean I describe everything as surgeries on Legendrian knots.
Yes.
So actually, in the background, we are doing transverse surgery. But because surgeries on Legendrian knots are more kind of people have better comfort with it, you can reinterpret transverse surgeries if done appropriately as some sort of surgeries on Legendrian knots. So indeed, when I was saying like, K has a Legendrian representative which has a fillable surgery, you could ask me what about you choose a different representative? It doesn't happen because precisely it is a transverse actual surgery. So different Legendrian representatives, they are related in a very, very understood way.
And what about the negative contact?
Well, negative one, as I just stated, like Yasha's result covers all of them. When you do negative contact surgery on
I mean, for negative contact structures, is there a difference between positive and negative?
I mean, I think there should be lots of kind of symmetry. You need to reinterpret things, but like it's like more or less like a very general assumption when you start understanding context surgery. Say, I will focus on positive ones. You might as well. I mean, I think there are lots of good questions to ask that, but some stuff will be parallel and there will be some differences, some of the complexity will translate different ways. So I would expect like, yeah. But like, I think it should be very interesting. This is maybe not what you're asking, but on a given contact tree manifold, looking both positive and negative contact structure should have more meaning than explored. So it hasn't been. I think that is sad. Anything else? Okay, I'm around if you will have more questions. So.